Bismillahirrahmanirrahim. Assalamu alaikum. Welcome to my YouTube channel. Today we learn about aldehydes and ketones. Aldehyde and ketones are the carbonyl compound, and carbonyl compounds are those compounds which have carbonyl functional group. Carbonyl functional group is that functional group in which carbon is double bonded to the oxygen atom. So we say that aldehyde and ketone both contain carbon double bond with oxygen atom. Now we talk about the importance of carbonyl compound. Carbonyl compounds are central importance to the organic chemistry, biochemistry, biology. They are used as a solvent, they are used as reagents, and they are used as a starting material for manufacturing of many other material. They are used as a constituent of fabrics. They are used as a flavoring agent. Like carbon has a mint flavor and it is used mostly in chewing gums. Similarly, acetophenone has pistachio flavor and it is mostly used in ice creams. And vanillin has a vanilla flavor and it is mostly used in perfumes and food materials. Carbonyl compounds are used to make plastic, like formaldehyde is used for manufacturing of bakelite, and many carbonyl compounds are used in drugs. Naturally occurring carbonyl compounds include protein, carbohydrates, nucleic acid that make up all the plants and animal. Simplest carbonyl compounds are aldehyde and ketones having general formula R C double bond O and H. This is aldehyde and R C double bond O R. Now this R can be alkyl group or aryl group. In aldehyde, one alkyl or aryl group is bonded to the carbonyl carbon, while in ketones, two alkyl aryl or one alkyl and other aryl group is bonded to the carbonyl carbon. Structure of carbonyl compound. The carbonyl carbon atom is sp2 hybridized and bonded to three other atoms through coplanar sigma bonds that are oriented at 120 degrees from each other. The unhybridized p orbital overlap p orbital of the oxygen atom to form pi bond. The double bond between carbon and oxygen is similar to alkene, but it is shorter and stronger and more polarized because there is a greater electronegativity difference between carbon and oxygen atom. Now we move towards the method of synthesis of aldehyde and ketones. Oxidation of alcohol. Aldehyde and ketones are obtained by oxidation of alcohol. Secondary alcohols on chromic acid oxidation yield ketone. This is a secondary alcohol that will react with sodium dichromate in the presence of sulfuric acid. We will call it chromic acid solution. This results in the formation of ketone. Oxidation of secondary alcohol take place and this would result in the formation of ketone. Now we can say that secondary alcohols can be easily oxidized in the presence of bleach, in the presence of HNO3, nitric acid, and this can easily be oxidized in the presence of potassium permanganate. Another example is shown in which oxidation of secondary alcohol is shown in the presence of chromic acid or bleaching agent, and this also leads to the formation of ketone. Oxidation of primary alcohol is usually done by different oxidizing agent because chromic acid or manganate or bleaching reagent converts primary alcohol to carboxylic acids. Here we see that a primary alcohol is made to react with PCC, pyridinium chlorochromate, and this leads to the formation of aldehyde. Good yield of aldehyde is obtained in this case, or we can use one DMP oxidation method for the oxidation of primary alcohol. We have discussed these reactions in oxidation of alcohol. Ozonolysis of alkenes. Ozonolysis followed by mild reduction cleaves alkenes to give ketone and aldehyde. Depending upon the structure of alkene, we can obtain aldehyde and ketone as a product. Here, alkene is made to react with ozone and followed by reduction with dimethyl sulfide leads to the formation of one aldehyde, other ketone, and dimethyl sulfoxide. Ozonolysis is useful synthetic process because yield is usually good. Friedelcraft acylation. Friedelcraft acylation is an excellent method for making alkyl aryl ketone or diaryl ketone. It cannot be used, however, on strongly deactivated aromatic system. If this G is hydrogen or an activating group that is attached on the ring, then Friedelcraft acylation is easier to be done because this acyl group itself acts as an electrophile. So in the presence of Lewis acid and water, this leads to the formation of ortho-substituted or para-substituted acyl product. Example is given in which para-nitrobenzoyl chloride is made to react with benzene ring in the presence of AlCl3 or water, and this leads to the formation of para-nitrobenzophenone. If we have to substitute a formyl group on the benzene ring, we could not use formyl chloride because that is unstable compound. Instead of formyl chloride, we will use a mixture of carbon monoxide and HCl that forms an intermediate which act as a formyl chloride and leads to the formation of formyl substituted aromatic ring. Like Friedelcraft reaction, the Gattermann-Koch formylation succeeds only with benzene and activated benzene derivatives, as this reaction is called as a Gattermann-Koch synthesis, and it is mostly done for the substitution of formyl group on the benzene ring. So toluene is made to react with carbon monoxide and HCl in the presence of AlCl3 or copper chloride, and this leads to the formation of formyl substituted benzene. Paramethyl benzaldehyde. Hydration of alkynes catalyzed by acid and mercuric salt. Hydration of terminal alkynes is a convenient way of making methyl ketones. This reaction is catalyzed by combination of sulfuric acid and mercuric ion. And the product is Markovnikov product. This initially formed product, that is enol, will readily tautomerize with shifting of proton and leads to the formation of ketone. Another example is shown in which enol readily tautomerized to form ketone because ketone is more stable as compared to enol. Hydroboration oxidation of alkynes. Hydroboration oxidation of an alkynes give an anti-Markovnik of addition of water across the triple bond. Di-secondary isoamyl borane called as a decimyl borane is used since this bulky borane cannot add twice across the triple bond. On oxidation of borane, the unstable enol quickly tautomerizes to an aldehyde. Example is shown. A terminal alkyne is made to react with decimyl borane in the presence of hydrogen peroxide and NaOH. It forms enol, and enol readily tautomerizes to form an aldehyde. This word isoamyl is used for actually isopentyl group. Amyl is the old name that is used for isopentyl structure. Another example is shown in which terminal alkyne is being oxidized to aldehyde. Synthesis of ketone from carboxylic acid. Organolithium reagents can be used to synthesize ketone from carboxylic acids. Organolithium are so reactive towards carbonyl that they attack the lithium salt of carboxylate anion to give dianion. Protonation of dianion form hydrates, and these hydrates readily loses the water molecule to form ketone. If alkyl lithium is a cheap compound, then we can use it in excess. Like here, the two equivalent of alkyl lithium, that is phenyl lithium, is made to react with cyclohexane carboxylic acid. This leads to the formation of dianion, and protonation of this dianion leads to the formation of hydrates, and this hydrate lose water molecules to form ketone, that is cyclohexyl phenyl ketone. Synthesis from nitrile. Nitrile can be used as a starting material for the synthesis of ketones. Carbon triple bond to nitrogen is polarized bond due to electronegativity difference between carbon and nitrogen. So nucleophile can easily attack on the electrophilic carbon atom of the nitrile group. And this leads to the formation of magnesium salt of an amine, which on acidic hydrolysis leads to the formation of ketone. Aluminium hydride can reduce nitrile to the corresponding aldehydes. Diisobutyl aluminium hydride is commonly used for the reduction of nitrile. The initial reaction forms an aluminium complex that hydrolyzes in aqueous solution. Nitrile on reaction with diisobutyl aluminium hydride leads to the formation of aluminium complex of iminium salt, and this on acidic hydrolysis leads to the formation of aldehyde. Another example is shown in which cyanide is being oxidized to aldehyde in the presence of diisobutyl aluminium hydride in acidic medium. Synthesis from acid chloride. Acids can be reduced to aldehyde by first converting them to functional group that is easier to reduce than an aldehyde, the acid chloride. We can easily oxidize aldehydes to carboxylic acids, but the reduction of carboxylic acids to the aldehyde is difficult because aldehydes are so reactive that they can easily react with the reducing agent and get converted into alcohol. So first we will convert them in suitable compound that can be easily reduced to aldehyde rather than being reduced into alcohol. So first the carboxylic acid on reaction with thionyl chloride will be converted into acid chloride, and now we say that this acid chloride will be reduced in the presence of mild reducing agent, that is lithium tri-tertiary butoxy aluminium hydride will get converted into aldehyde. Here the normal reducing agent, that is lithium aluminium hydride, that is not used because it will reduce the acid chlorides into alcohol. Reduction of acid chloride with lithium tri-tertiary butoxy aluminium hydride gives good yield of aldehyde. Another example is shown in which isovaleric acid is first converted into isovaleroyl chloride, which on reaction with lithium tri-tertiary butoxy aluminium hydride will get converted into isovaleryl aldehyde. Ketone synthesis. Grignard or organolithium reagent adds to the acid chlorides to give ketone, but they add again to the ketone to give tertiary alcohol. Acid chloride on reaction with alkyl magnesium halide is forming ketone, and ketone then again react with another molecule of alkyl magnesium halide to form alk oxide that can easily protonate to form alcohol. To stop at the ketone stage, a weaker organometallic reagent is needed, one that reacts faster with acid chlorides than ketone. Lithium dialkyl cuprates and other organocuprates react with acid chlorides to give good yield of a wide variety of ketone. Lithium dialkyl cuprate on reaction with acid chlorides form ketone, and we say that lithium dialkyl cuprate is formed by the reaction of two equivalents of corresponding organolithium reagent with cuprous iodide. So example is shown in which butyl chloride on reaction with two equivalent of lithium and copper iodide leads to the formation of lithium dibutyl cuprate, and this on reaction with benzoyl chloride leads to the formation of butyl phenyl ketone. Synthesis from ester. Diisobutyl aluminum hydride reduce ester directly to aldehydes at dry ice temperature, about -78 degrees centigrade, unlike lithium aluminum hydride, which reduces esters to primary alcohol. Cold diisobutyl aluminum hydride usually does not reduce aldehyde further. The initial reaction forms an aluminium complex that is stable towards further reaction but hydrolyzed to aldehyde in aqueous workup. So esters in the presence of diisobutyl aluminum hydride at -78 degrees centigrade form initial an aluminium complex, and this aluminium complex form an aldehyde. Another example is shown in which ester is being converted into aldehyde. So this is all about the synthesis of aldehydes and ketones. In the next video, we will study about the reaction of aldehyde and ketone. Thank you so much.